All right, physical science students. I was informed by some people this morning in our Zoom sessions that my videos are too long. Well, there's nothing I can do about that. I mean, I got to tell you what I got to tell you. So, hey, it just is what it is. So, watch only the parts you need to watch. Now, here's the deal with this. I am sitting outside right now on our deck. And you can probably hear the birds chirping, singing in the background. I don't know. Anyway, numbers 1 through 4. Here we go. Written description to describe the motion of this object. Now, first of all, you have to look at what kind of graph it is. It is a position-time graph. What do you know about position-time graphs? The slope means what? Velocity. The slope of this graph is telling you velocity. Well, what is the slope? Well, it's a curve, so it doesn't have just a single slope. So what does that mean? It means the slope is changing. And if the slope is velocity and the slope is changing, then the velocity is changing. Now, how is it changing? Let's look at the remember the tangent situation? Remember, the tangent is a line that touches only a single point on the curve. So that's kind of a tangent at, say, that point. That line touches the curve only there, and it tells us that at the very beginning, the slope is what? Very steep and positive. Steep meaning fast, and positive tells us the direction. So this object is traveling very fast at the beginning. Right? Are you all following here? Very fast. Now, sometime later, oh, that was kind of a bad one. That's kind of bad. I guess that's okay. So that tangent is not as steep. Oh boy. That tangent is not as steep. So that means at time, what is that around? A little after 2 seconds, it's not as fast. And how about out here? Oh my gosh. Oh my gosh. Jeez Louise. There we go. There we go. That, let's say time maybe just after 8 seconds, that tangent is even less steep. So again, the steepness is decreasing. It's getting less steep. And if it's getting less steep, what does that mean? Less steep means what? If it's getting less steep, it is slowing down. Okay, it is slowing down. Now, what direction is it going, though? Well, these slopes, that's a positive slope, that's a positive slope, that's a positive slope. On a position time graph, which way the line is tipped tells you the direction. So it's positive direction, slowing down. So slowing down, it is positive direction though. Positive, oh my gosh, this thing is positive direction. This thing, oh my gosh. Positive direction. So slowing down, positive direction. Now, where does it start? Now, because it is a position time graph, we can see that. It starts at the 0 position, already moving fast. So, written description starts at 0 Oh my gosh. 0. Oh my gosh. Position. Oh my, this is terrible. Starts at 0 position. Fast. In, oh my, in positive direction. I'm going to abbreviate. In positive direction. Slowing down. There. How about that? There you go. Oh my goodness, that took 5.5 minutes for one question. Draw the motion map for the object. All right, well, here's the deal. If that's our 0 position, positive direction, where did we say it started? We said it started at the 0 position, but moving very fast. Moving very fast in what direction? Positive direction. And then, let's say 2 seconds later, how fast was it? Not as fast. 2 seconds later, how fast was it? Not as fast. 2 seconds later, how fast was it? Not as fast. And then 2 seconds later, how fast was it? It wasn't moving. Oh, look at that. 2, 4, 6, 8, 10, 10 seconds. That's what our graph shows. And that's what we see on the motion map. Now, we have to have an A. What direction is the A? Now, if you remember from a video I had before that maybe some of you probably never watched, the A always points to where the larger arrow is. Okay? Has to be this way. It's a negative acceleration with a positive velocity in this case. Now, you can think of it in one of 2 ways. Because the arrows are getting shorter, A has to be in the opposite. Because the velocity arrows are getting shorter, A has to be opposite direction of these arrows. But again, it's pointing toward the longer of the arrows. That's another way to tell. All right, number 3. Sketch the VT graph for the object's motion. Okay, VT graph. Now, I want you to think about what we already said. What did we say up here? It's positive direction, so that means the line on our VT graph has to be up here. How do we know? Because it's traveling in the positive direction. These slopes are positive, which means our line has to be where positive velocities are. It has to be up here. It cannot be down here. It has to be up here. And it starts with what? It starts fast in the positive direction. Where is fast in the positive direction? That's up here. That's where fast velocities are. Not 0, but fast velocities up here. And what's happening? It's slowing down. Oh, so it starts fast to positive and slows down. So that's going to look like that. Boom! Now I want you to notice something. What kind of slope does this have? Negative slope. What kind of acceleration do we have? Negative acceleration. Ah, coincidence? I think not. That's how we know. If this slope on the VT does not match what your A is, then something's not right. Either that's not right, car just went by. You hear that? Either the A's not right or this graph is not right if they don't agree. If that's a negative slope, that's got to be a negative A. If that's a positive A, then this has got to be a positive slope. Now again, whether the line is up here or down here depends on what direction you are. Remember, positive direction, line's up top. Here it's positive slope. Here, line's up top. If it's a negative direction, this graph will have a negative slope, and the line has to be down here. So positive slope here means line up top. Negative slope here means line down the bottom. Hope that makes sense. All right, number 4. This is like the motorcycle question. All right, motorcycle question. Here we go. We have acceleration is delta V over delta T. It is the change in velocity over the change in time. Okay, change in velocity over the change in time. How much did the velocity change? Well, it started off going 50, and then it stopped. Started off going 50, and then stopped. That means its velocity changed by how much? By 50 meters per second. However, it started with 50 and ended with none. That's a change that's negative. Now, I'm going to remind you of this, which you may have forgotten. Oh, darn it. Final, or I should say end minus start. Isn't that always how we said it before? End minus start. Let me change that. End, the velocity at the end, minus the velocity at the start. That's end of 0 minus start of 50. Oh, geez. Meters per second. What's 0 minus 50? Negative, negative 50. All right, that's why the negative sign is there. Because 0 minus 50 meters per second is negative 50 meters per second. Now, what is the delta t? How long did that take? That took 10 seconds. That took 10 seconds to do. So we put our 10 seconds down here. 10 seconds right there. And what does that give us for an acceleration? 5 meters per second for every second. And that's negative. That means the velocity is changing by negative 5 meters per second every second. Hope that makes sense. There we go. Numbers 1 through 4, and it took 12 minutes. Holy mackerel. Holy mackerel. Next slide. Probably be a whole nother video. I'll probably have to break these down into separate videos here. You're welcome. Okay, 5 through 7. So we have a VT graph. It says, what is the acceleration of the object in the graph at left? Show work. How do you find acceleration on a VT graph? That's the slope. You need the rise and you need the run. And you might as well just use the whole thing because it's easiest to read that way. I mean, it goes to an intersection, right? It starts at a 0 intersection here and it ends at this intersection, so you might as well just use the whole dang graph. Now, question is, how big is the rise? Now I want you to think about this. The rise is the delta V. It's the change in velocity. That's what the rise is on the graph. So in that problem we just did, number 4, the delta V, it was given in a word problem, word question, not a graph. Now we have a graph telling us the same thing. How much did the velocity change? How much did the velocity change? It went from 0 to what? 25 meters per second. So it changed by 25 meters per second. Positive this time. Positive this time. And how long did that take? Well, started at 0 seconds and went to 8 seconds. That took 8 seconds for that to happen. So what's my acceleration? Well, it's 25 over 8. So like 3.125 meters per second for every second. That means, again, the velocity is changing by 3.125 meters per second faster every second that goes by. Okay, write its equation of motion. And again, I just mean the equation of the line, because the line represents the motion, and so the equation of the line is the equation of motion. I know some people were confused by that, but it means the same thing. The equation of motion is the equation of the line. Now again, we're talking about y equals mx plus b. What's the y part? The y variable, velocity. Velocity equals m. What's the m part? Slope. We just found it. 3 point, oh boy, I'm going to put parentheses, 3.125 meters per second for every second, parentheses. That's a C. That's a C. And what's the x variable? Time. Time goes in right here. What's the y-intercept? Nothing, because it crosses at the 0. So we don't have a y-intercept. There's your equation, including units, right there. How fast would it be at 15 seconds if this continues? So if the motion that you're seeing right now continues on for 15 seconds, we don't have 15 seconds on our graph. It stops at 8. So we're talking 15 seconds like out here somewhere. So that line would be way up going like this, and we don't have that information here. You can't read that on the graph because we don't have that high on the graph. So what do? We take the 15 seconds and we substitute it into the equation we just wrote. Velocity equals, bye, my family's leaving. Where was I? Oh yeah. Velocity equals 3.125 meters per second for every second, parenthesis, times time. Instead of the word, now I'll put my 15 seconds. 15 seconds. Boom. Notice, that second cancels the bottom second, and I get what? 3.125 times 15. Oh no, I don't know exactly what this is. Well, 15 times 3 is 45, plus an eighth times 15 is 1 7/8. So that means 46.875. I think I'm right. I think I'm right on that. And that is meters per second. Because again, that second goes away. That got canceled by this one. Blackbirds. All right. 46.875 meters per second. There we go. Got that. Have we got that? Now, if you look at the graph here, wow, that can't, what the, that can't be. Is that right? Yeah, the way I've drawn it here, that's way off. That can't be. Is this right? It's got to be right. 15 times 3 is 45. Plus another 1 point. Yeah. Yeah, it's got to be right. I'm just looking at this and saying, okay, right about there's 46 on this graph. And that would go over here like this. Like right there. That doesn't seem like 15 seconds. If that's 8, well, I guess, maybe it is. Maybe I had that way too far over. Okay, anyway, I'm wasting your time now. All right, so this is probably going to be a whole separate video, or maybe I had to put the first two together. I don't even know. I don't even care. Here we go. That was beginning or the end of the first page. Moving on to the next slide.